Today I would like to talk about ML coding for logistic regression. In an ML interview, you might be asked to implement logistic regression using NumPy. And before doing the actual implementation, we want to understand what kind of problem can this algorithm solve. And this algorithm usually takes a bunch of inputs and then make one prediction between 0 and 1 or true or false. It is a binary classification algorithm. It can be used for fraud detection, for example, where you can tell if it's a fraud or not, or it can be used for detecting a disease. If a patient has a certain disease or not. And this algorithm itself, it is trying to minimize the so-called binary cross entropy. And we do not need to memorize this equation, but usually during an interview, at least, you have to be able to tell the interviewer that this target loss or optimization target is the binary cross entropy. Instead of the MSE, which is usually used in linear regression. And the optimization method we use is usually the gradient descent. Essentially, we compute the partial derivative of dl and d omega. Usually, instead of d, we use partial derivative, and this is denoted as d omega. And here you will use like chain rule. You will not be asked to derive these things usually, but at least you should be able to point out the way you derive it. And once the gradient is computed, similarly we compute the dB, the bias, partial derivative of that. Once the gradient is derived, you could use like gradient descent to update your weights, which is like your weight minus a learning rate times the gradient, and b is equals to b minus lr times dB. And to make the picture complete, you will have a weighting factor where this accept an input x, and then usually you might be having like x multiplied by the weights, then adds the bias, form a z, where here you have a sigmoid activation function, and then this gives you like the y height, the prediction. And usually this x is in dimension of n and d, where n is number of samples. D is the number of features. So one is sample dimension, one is feature dimension, where omega weights is in the shape of D. So each feature has a weighting factor, and B is the same, and Z is the
So the B is actually a scalar. Sorry. And
here I made a mistake. The B is usually a scalar, which will be broadcast, such that this is n, because you are using a matrix multiplication, D times D multiplied D will gives you like n, and then scalar broadcast gives you n, and then the y here is also n. So each sample will have its own prediction. And we also want to know like when this algorithm will fail, right? Knowing when it fails, you know when you should not use it. So this algorithm is only applicable if your data is linear separable. So if you have a lot of nonlinearity, this algorithm alone will not be able to, make good prediction. Although the sigmoid itself, introduce a little bit nonlinearity, but your Z is still kind of a linear combination of the features. So if the relationship between y and your x has a lot of nonlinearity, then this algorithm will not be able to do its job. You will need to do a lot of feature engineering in order to, represent the x passing in this stage. You might have some prior stage that you need to link your raw inputs, doing some kind of nonlinear features. You cannot directly use this algorithm if there's large nonlinearity between x and y. And then something called collinearity. It also does not apply. And if it has a severe class weight bias, meaning the class distribution is not even. You have just a few negative samples for in y. You might need to do additional work before applying this algorithm. Knowing that, we will start implementation. This is what you're gonna be challenged in an interview to implement this algorithm. Usually the the coding part is easier. The hard part is the thinking. We need to think following certain patterns. First thing is like what kind of parameters, right, or configs this algorithm is needed from the user. One thing is the learning rate. That's how fast you do your gradient descent. So start with the default value 1e minus 4. And then for optimization, usually you will have some like max iteration. This could be like 10,000. So after 10,000 iteration, if nothing stops the algorithm, we would stop it, and this is usually configurable. And then we usually also have something like tolerance for stop criteria. This could be initialized to 1e minus 5, for example. And there are different methods to apply this, but I chose to use gradient. I chose to use gradient norm because I do not want to compute the loss, the entropy loss, cross entropy loss explicitly, which is usually expensive computation. So that means I'm calculating the gradient, and then I'm calculating the norm of the gradient. If this one is less than the tau, I would stop optimization. And then after thinking about the parameters, we would think about what to do in initialization. And for this algorithm, the initialization is not that complicated. You can just initialize everything to be zeros for your weights. Of course, the size has to be like nd, which n is the number of samples, d is the feature dimension. Sorry. This weighting factor is only d1, right? Actually d. And b, the bias, is a scalar, which could be initially 0.
And initialization, we could also use randomized initialization for omega.
But 0 is okay for this specific algorithm. After initialization, we will think about fitting, essentially the training process. For this specific algorithm, the training process would essentially be like, our kind of max iteration defined. Each iteration we would do forward propagation, which is essentially using the y hat equals we can separate into multiple steps, like your z is equals to the x multiply the weights. Again, the weight is like d, the x is like nd, so the whole thing becomes like n, right? And then plus the b, which is the scalar broadcast. The z would end up to be shape n, and then the y height is equals to sigmoid z. And here, after like initialization, we could think about another step that is called utility function or supporting function, right? When we write this whole stuff, there might be certain things we want to implement as a function, so it can be reused at multiple places. One of such function is the sigmoid, which mathematically is 1 over 1 plus exponential negative z. And now going back to the y hat sigmoid z, we do forward prediction, and then we need to compute the error, which is your y height minus y. Let me check if it's this definition is also kind of important. Yeah, the error is defined as y height minus y instead of y minus y height. And after computing error, this is the equation that you want to memorize, because you don't want to derive the whole chain rule stuff. You want to memorize this for interview. And the d omega is equals to the x multiply the error, then divided by n, which is number of samples. And here there is a trick you can use to match the dimension, because z is like n, y is also n, and y height, y is also n, so the error is also n. The error is n, while the weight, the d omega, dw is the same shape as w, which is actually d, right? So in order for this to be a d, we would need this item to be dn. So that's exactly x transpose, which is x dot t. So this equation is what you want to remember for logistic regression, and dB is equals to the mean value, which is here. I would just sum up all the errors, which has n, and then divided by n, which is the mean value of the error. That is your bias. So these two equations worth memorize. After that, it's pretty standard. Gradient descent, d omega equals omega minus, which is the LR times d omega. Actually, this is your new omega. And then b is equals to b minus LR times dB. This is like updating the width and bias. So forward propagation, and then compute the error, and then compute the gradient, and then do the gradient descent, and then charge your stop criterion, which is like if this is the max iteration stuff is explicitly or implicitly implemented. So we would just say like if the norm of d omega, which is gradient norm, less than the tau, we would break the loop, and then end of the day we want to return some, outside the for loop, and we will use class object-oriented programming, so this would be kind of return the self. That's where we fit the algorithm to learn the weights and bias using gradient descent. And then after the fitting, we would write a function to predict. And specifically for this logistic regression, you want to also write a function that is predict probability. That is where you want to define a predict prob on x, and then returns a value between 0 and 1, right? That's kind of your probability, and that is very easy, which is essentially this part goes here, right? And then you want to also write a function that is finally do the predict and returns the x and y, right? I mean returns the 0, 1 or true or false. So that one is like your y height is equals to the predict prob, and that gives you a number between 0 and 1, and then you will charge based on y height larger or equals than a threshold, which could be 0.5, or you could even pass some parameters to change it. This could be as type int or boolean. That is the whole process for the pseudocode, right? So we need to think about the what kind of parameter configurations, how to do the initialization, how to do the fitting, as well as the stop criteria, and what kind of supporting function you can write for reusability, and also you want a prediction function for the user. This pattern can be applied to other algorithms that we're going to write in the future. And one most important thing is when we try to implement this during coding, we want to use NumPy in a way that is NumPy vectorization. This is something the interviewer will challenge you as well. For this specific example, it is the way that we use the matrix multiplication, and also the way we use like broadcast. Those techniques kind of avoid the needs for using more for loops, because when we are doing this x multiply matrix multiply omega, because omega has like actually d element, I'm just making it up like omega 1 up to omega d, right? And then this x is like n to d matrix, and we could have like x 1 1 all the way up to x1d, and then x n1 all the way up to xnd. And if we don't have this kind of vectorized operation, you would need to first compute this one multiplied by that plus dot dot dot, that one multiplied by that, and then you would essentially use a for loop to loop through like each row of this and multiply with the corresponding weights and then sum all the stuff up. That will be a nightmare. So yeah, and knowing all this, we could essentially goes into the actual implementation. The actual implementation is very simple once you understand all the basics. Here I have my repo, and then inside the linear, I wrote the linear regression, where essentially user parameters includes the threshold, the linear, the learning rate, maximum iteration, tolerance, and this is pretty standard initialization. And we want to write a function for supporting function for sigmoid, and there's one trick for implementation where sigmoid you have this function, and because the exponential function is something like this, if it's a z experiment z, and then because we have the negative z, so it is essentially the opposite. For kind of numerical stability, usually what people do is like, even z is like infinite, or negative infinite, we would always clamp this to be negative 500 and 500. You can have that or not. That's numerical stability kind of implementation details. And then initialize, we use NP zeros to initialize the weights. For the fitting, we make sure this shape is like D, actually N. So instead of N1, right? So, and then we assert the y dimension to be 1 and x dimension to be 2, and this is pretty straightforward, following our pseudocode. For all the iterations, we use vectorized operations, matrix multiplication, and then do the sigmoid, have error. Again, this is something you want to memorize for logistic regression. I would say this you want to memorize for interview. And then gradient descent, check for the stop criteria. We predict probability using the forward propagation equations, and then do the prediction, final prediction given the labels. And then inside the notebook, I tested this a little bit by, treating it as a whiteboard: layout, config parameters, initialization, supporting functions, fitting, as well as predictions. And then this enables kind of a auto-loading for the notebook, such that when I change the algorithms inside the logistic regression, I do not need to restart the kernel. But here we import that from our package, and I also wrote a little bit supporting utility functions that essentially here you based on the seed, you can get like a default random generator. This is important for reproducibility, and here we are using that get a random generator, and we are able to make certain x, and we are able to get certain weights, and we calculate the logits based on the equation, and assuming the bias is 0, and we have calculate the sigmoid probability and get some y. And imagine if noise is 0, then your y is exactly the y. So this is a function that I use to kind of generate some test data. And for demo purpose, I'm setting the seed to be 42, threshold to be 0.5, and this is the x it gives you. Every time will be the same because we have the seed. And then the y it makes is again the same, and we initialize our model by setting the tolerance to 0, such that I can sort of overfit to it, and call the model for fitting. The prediction comes like that, and this is the ground truth. They are the same. The accuracy is 1. So I wrote a PyTest as well. Here the PyTest test logistic regression, where grab the default generator, and I'm just instead of using the generator that I wrote, I just quickly wrote up a test that does not depend on other packages. So I created 100 samples with 2 dimensions, and each dimension, if its first dimension is larger than the 0th dimension, it will return a true. So I use this simple rule to make up the y, and then load the model again with tolerance equals to 0, fit the model, get the prediction, and make sure the accuracy is larger than 0.7. So this test is essentially test if everything is okay, our model after fitting should at least perform better than the random algorithm. Like if you just randomly charge if it's true or false, you end up with 0.5, right? So your accuracy should be larger than 0.5. This is a PyTest. Essentially, if I do PyTest, test logistic regression.py, we can see that the test passed
because our accuracy is larger than 0.7. Okay, that concludes the logistic regression for interval. And next time we're gonna write some new algorithm.